First, I apologize for having to speak in English. After having come to Japan for about 30 years, I finally concluded that the language is impossible. I'll try to speak slowly. I'm going to have relatively few slides, very simple, and I'm going to spend some time playing here, probably not running any jobs, although maybe we could do that too. What I want to do is to touch on just a few of the new features in the current version. There are literally hundreds of small changes. I want to touch on two of the more important of those small changes. The first one being the ability to interchange 2D and 3D basically seamlessly. We've been able to do that not seamlessly for a long time. I'll just touch on that. And then I also want to touch on my view of how output should be displayed, how one should access properties. I much prefer pictures rather than words, but if you have to use words, it's better to try to put them into clean summaries. I'll just demonstrate that that's basically something new. On the more serious and deeper vein, I want to touch on three things. One is density functional theory. We're heading there, and why. And that's the most academic sort of topic I'm going to talk about. I'll give a basis of what density functional theory is and how all these hundreds of different methods really relate to each other or attempt to. The second topic is conformational analysis beyond molecular mechanics. How do you determine the shape of a molecule and also what are the low energy shapes of a molecule? Previous to this, and pretty much everyone has not moved beyond molecular mechanics because it's really too hard. And I'll try to show you a way of thinking about the problem that makes it a little bit easier and maybe almost routine. I'm going to use the conformational analysis section to talk about NMR spectroscopy. In particular, I want to discuss how it can now be applied not only to static molecules of fixed structure, but also molecules that are flexible. So how you can combine in a relatively routine and hopefully easy way dealing with that. I'll mention DP4 analysis, which is a statistical tool to try to understand whether what a experimental spectrum fits, which it best fits, which of several related structures, for example, stereoisomers, it best fits. And then I'll give an example of using natural products. Interchange of 2D sketches and 3D models. Spartan, for a long time, as I mentioned, could either build things in 3D, that was its origin, or draw things in 2D. And for quite a while, those two worlds were quite separate. You either did one or the other. We can now sort of merge them cleanly and try to use the 2D models that we get out as things we can insert into pictures. I don't mean 2D sketches as competing with a program like ChemDraw. Those programs are, by the use of templates and the like, are produce extremely beautiful drawings. We're not attempting to do that. I'm attempting to construct input for doing calculations, but also to perhaps display those. Let me jump into Spartan. Okay, as I was getting to the sketching notion, if you were to sketch something, let me build something with a 7-membered ring, just anything. And I now bring it out into the real world. One, I can now go back. So I can go back and forth. I can now, okay, here's a cleaned up sketch. I can now go back and forth painlessly. So if I wanted to change this, I could go and do it. Secondly, what one can do coming into the 3D world, I can come under Properties dialog, and we can look at its drawing, and we can say, here's the drawing, copy it, or save it to something. Again, this is not intended to be ChemDraw. And to now, if I were to want to paste this into something, so if I had, for example, if I had a spectrum, if I wanted to paste this diagram onto a spectrum, Okay, if I want to take this and paste it into a Spartan plot or a Spartan spectrum, I could do that. The other thing I want to demonstrate is that we now have the ability to take output and look at it in a summary form. If I come here and I have some object, let me build something really simple now. If I have something really simple and I do a calculation of some form, let's just do a structure at, I'm just trying to do something really, really simple, and do an IR spectrum, anything. Okay, when that's done, shouldn't take very long. I can now look at that spectrum in the spectrum dialog, as we've been able to do for a long time, so I can now plot that. This is rather old. I can now take the structure, which is missing hydrogens, of course, so it's not very interesting, and I could copy that and paste it. That's not very exciting since it's only 2 heavy atoms. I can paste an image, so into a diagram or to a plot, something like that. The thing I want to demonstrate here is that the output here is now in a much more organized way. This is a tab called Summary, and that tab has in it some switches. So, for example, there's a switch which says turn on the information about the infrared Raman. So the data there, before you had to look at the output or go to the spectrum, which is pretty inconvenient. Or turn on thermochemical properties, enthalpy, entropy, and Gibbs energy. Turn on properties. Or you could turn them off. So this dialog is designed to be very non-complicated in a sense. And any property you calculate, whether it's something that's automatic, like atomic charges, will be displayed in this way rather than some continuous stream of information. These are HTML documents, so they can be dealt with rather simply. The next topic, so this is basically summaries. These are superficial changes, but important ones from the perspective of users. Okay, let's go back to PowerPoint now. One of the ongoing application areas is density functional theory. This has replaced almost every other method in the last 10 or 20 years. Hartree-Fock theory is really something that's not really employed any longer, with one very important exception, which is to get very cheap, reasonable structures for molecules, or at least reasonable guesses. Theories beyond Hartree-Fock theory, things like MP2, have largely disappeared. Higher level theory, things like that are called couple cluster theories, are now used as to gather standard data. But density functional theory is really the dominant scheme. Now, it's pretty dense, what it's made of, but essentially it can be broken down into an expression which is dependent, the energy of a molecule is dependent on the electron density and on the derivative of the electron density. So if I take an object and I calculate the density, that's a unique property of the positions of the atoms and the number of electrons, and I calculate the derivative of the density at every point on giant grid. The simplest density functional models are an expression in those two quantities. That's called the generalized gradient approximation. First generation models are all of this nature. They're really no longer used. First set of models that is presently used are called global hybrid models, or global hybrid generalized gradient approximation models. Big words. What that really means is that we're going to put into this expression of dependence on the density and its gradient. We're going to put in also a dependence on the exchange energy from Hartree-Fock theory. That's a costly step, but it leads to a rather significant improvement. You can either put that in as a constant, which is called global, or you can put it in as a function of the density, which is called range separated. Okay, so that's the first approximation is the global gradient, generalized gradient approximation. The second one is whether we put in the Hartree-Fock term or not, and if we put it in, do we put it in as a constant or a variable? The third step are a set called meta-functionals. I'm going to show this in a diagram in a second, which will make it a little easier. The third one are called meta-functionals. What they are is, in addition to the gradient, we're going to throw in the derivative of the kinetic energy. And that is essentially the second derivative. It's not quite, but it's related to the second derivative. So we're going to think about the terms in not only in terms of a density or a gradient, but also second derivative. Those are called meta-functionals. The last step is to think about what happens when you get electrons that are far away. Long-range interactions, these are dispersive interactions. This is why helium comes together. Long range, there's actually attraction. You can either account for that not at all, empirically, or actually do it correctly. Okay, those three things put together can be looked at in terms of a diagram. Okay, this looks horrible, but it's not so bad. We're starting from this globalized gradient approximation. This is the function plus its derivative. Okay, the meta ones are the function plus derivative plus something that's related to the second derivative. So those are the roots. You now say about Hartree-Fock exchange, you either forget about it, you include it as a constant term, or you include it as a variable term. That's the second class. The third class is what do you do about long-range interactions? These are dispersion. You either forget it, include it empirically, or include it by calculating it. Here are some popular functionals. There are hundreds of them in the literature, literally. B3LYP is formed by no non-local, fixed exchange, and generalized gradient. Probably the most popular functional. It's actually not very good in the general scheme of things. The one which I prefer as a general tool is a terrible name, omega B97XD. This is just the generalized gradient approximation, no second derivative term. Fixed exchange, but now put in empirical non-local. Okay, the other functionals follow from these. The best one in this set is this one here. And they get progressively, from here to here, down to here, they get progressively more costly in application. Which functional is best? This depends on what you want to do. Quantity of interest, it depends on the accuracy you believe you require, and it depends on practical considerations, how much computer time you want to spend. Absent from this are human considerations. It's no harder to use good methods than it is less good methods, where the difference is how hard the computer has to work. There's at least an order of magnitude between the simplest of the functionals that I listed, B3LYP, let's use that one, and the most costly that I listed. There's probably a factor of 10 in computer time. No difference in human time between those. Depending on task, you can get away with different functionals. Geometry is very easy. It turns out it's one of these properties that's quite simple to get accurately. Almost any functional will do a good job. B3LYP is perfectly fine with basis sets as small as this one. There's no reason to go to more sophisticated methods than these or to larger base sets if the task is really structure. There is one caveat to this, and that's in dealing with transition metals. It turns out that B3LYP is not very good, whereas this one is actually quite good. I'm talking about organometallics as opposed to inorganic compounds. When you talk about energy, the game is quite different. Reaction energies, things like isomer energies, are much, much harder to obtain accurately than structures. The functionals I mentioned, B3LYP, the omega B97XD, are not very good, where you have good experimental or good theory comparisons. You need functionals that take account of these long-range terms, not empirically, but analytically, actually trying to do them from a theory. You need basis sets that are significantly larger. This is about the smallest thing you can get away with. And so energy calculation is maybe 1 or 2 orders of magnitude more costly than structure calculation, although you only have to do it once. You don't have to do converging to a structure. It turns out that none of these methods are perfect. In at least my community, trying to develop methods that are really very good. Now you run into a big roadblock. You run into the problem that experimental data, thermochemical data, is one, not very common, except for really tiny molecules, and it's not very good. And this has been addressed in the last decade by doing very, very high quality calculations on very small molecules and trying to get accurate thermochemistry much better than experiment could possibly actually get at this point. That has led to the knowledge of deficiencies and the continued quest of improvements. And the current stage of improvements are called double hybrid functionals because the community doesn't really know anything about nomenclature. These are methods that, in addition to the dependencies that I showed before, also bring in a dependence on the unoccupied molecular orbitals. What we have here is a dependence on the density, the first derivative, the second derivative. We have a description of, we add Hartree-Fock theory in a very invariable way. We put in dispersive interactions analytically. Now brings in count for unoccupied orbitals. So it's another question, but there's only one line. These are very messy. It turns out that when you apply this current generation and the one which is now implemented in Spartan, there are actually several, is got a terrible name. It reduces reaction energy errors by about 20%. That doesn't sound like much, but it reduces absolute energies, things like absolute activation energy, by about a factor of 2. So it's a rather significant improvement. We're getting to the point where one can apply methods that are practical. They're expensive, but they're practical to get thermochemistry probably within 1 or 2 kilocalories, which is actually below what I would say is experimental measurement limits on which are available only on the very small molecules. Now I want to switch topics. Okay, conformational analysis. This is an area where we've spent a great deal of time, and the first fruits of that time showing up in this version of the program. Despite what people in my world, the theorist types, tell you, most molecules are not rigid. Most molecules are flexible. They're flexible because they have rotatable single bonds and flexible rings. So everyone's accustomed to a 6-membered ring chair boat, but as soon as you get 7, 8, 9, 10, it gets very messy. So we have molecules that typically will have tens or many hundreds or thousands of different conformations. While only a few of those conformations actually count as far as contributing to an energy or to a property, the reality is that you have to find those few. And to find those few and to order them, to say this is the lowest, this one is higher by some number, is actually a difficult problem. What's known experimentally? Well, the conformations of literally several 100,000 molecules are known as crystalline solid. This is one of the most organized literatures in chemistry, the crystallographic literature. On the other hand, if you go into the gas phase, so you replace crystallography by infrared or NMR. By gas phase, I really mean that or dilute solution. I treat those in a similar vein. The conformations of the equilibrium conformations of very few molecules, maybe 100 or 200, and they're all small, are known. One of the problems is there's almost no overlap between this set and the crystallographic set. Small molecules tend not to crystallize, and big molecules are too cumbersome to actually do anything with. And so we really don't know very much about what crystal packing does. We have some ideas, but we really don't have a quantitative feeling about how packing affects structure. We know in the case of hydrogen bonding, something that an isolated molecule will form a structure that is maximally hydrogen bonded intramolecularly, whereas the crystal it may or may not. We have good calculations for maybe 100 molecules where we know from good calculations what the structures are. Almost all of these are 1 degree of freedom, things like 1 butene, really simple things. There are only a few, less than 5 molecules with multiple degrees of freedom which are small enough to do calculations on. I'm going to use one of them as an illustration. What do we know about alternative conformers? What conformers are not the lowest energy, but are maybe low enough in energy to actually contribute? From crystallography, nothing. Only one conformer crystallizes. It's very rare to see a crystal with 2 different conformers. It does happen, but it's very rare. So crystallography tells us nothing about alternatives. In the gas phase, we know conformational differences for maybe 50 molecules, 1 butene CH eclipse versus CC eclipse, things like that. Very simple. Butadiene trans versus it's not cis, it's twisted cis. Very few molecules. We know almost nothing to nothing about molecules with multiple degrees of freedom. I think the only example I know is pentane. From calculation, we have, again, about 100 small molecules where we know the differences between low energy and higher energy conformers, 2 conformer molecules. We have a few, again, less than 5 molecules where we actually have multiple degrees of freedom. For a long time, the only tool that was really available was mechanics. There are 3 or 4 different used variants of mechanics now. They're all pretty much similar. Spartan uses the Merck force field MMFF, which is now 20 years old. This was explicitly parameterized to reproduce conformer energy differences. That was the primary goal. But now there is significant evidence to suggest that it's not very good. Let me just give you one example. This is based on very good theory. The molecule is melatonin. It has a few degrees of freedom. You can rotate around the methoxy group and you can rotate around here. It really doesn't have any intermolecular hydrogen bonding, so it's not really that exciting, but that's the biggest thing that's actually available. If you look at the reference, this is very good calculation. There is no experiment. Versus mechanics, it's not a scatter plot, but it's getting pretty close. The other couple of examples that are known are not this big, and they show similar dependencies. They're not scatter plots, but they're pretty bad. Cheap theory. Mechanics is very inexpensive. We could apply this to much bigger molecules with literally tens of thousands of conformers. So this is practical, but it's not very good. The other cheap theory is semi-empirical theory, which I really don't talk about very much, but I can't resist giving one slide. This is the same molecule. This is PM3. It's complete trash. So basically one could say I'm going to use a quantum mechanics model, which it is in a sense, but it's garbage. The lesson here is to basically try to, before one uses something, to try to calibrate it. And we now, in the last decade, have a very few number of reference compounds where someone has actually taken a huge amount of computer time to generate extremely good theory. There is no experiment again. The first theory that shows a little bit of promise is B3-lit. It's better than mechanics, but it's not perfect. Focus on the bottom square. The only ones that count are between up to about 10, this is kilojoules, up to about 10 or 15 kilojoules is what counts. Everything else is who cares. It turns out if you apply this is a very giant basis set. If you apply the best of the current functionals, and I could have put this with the double hybrid, but you don't have to go that far. That's one of the best of the current functionals. Big basis set, it's really rather good. It's essentially perfect. Now, the trouble here is that because of that basis set, the number of functions, because of that, this is really costly. And even to do whatever it is, 50 or 60 conformers of a molecule as small as melatonin is pretty tough. You can take this and you can make some simplifications to lower the cost by perhaps 1 or 2 orders of magnitude. You can take this rather giant base set and replace it by something still pretty big, but very much simpler. QZ means the Q is quadrupled. It means we're going to take the valence part and break it into 4 pieces. This is TZ, which is the valence part, which is 3, 1, 1, so the 3 pieces. So you're reducing that. You're also reducing the size. The other giant approximation is called the dual basis set approximation. These are all things that are fancy words, but they're automated and well-documented approximations. What this does is say, this is too big to converge on the wave function. All these procedures are iterative procedures. They're things which settle down to a solution. Instead of converging on this big thing, we're going to converge on something much smaller, and then we're going to do a single iteration, one more step with the big one. That turns out, in dealing with things like conformational energetics, is almost not noticeable, although you pick up a large factor. If you do those two together, you get a plot which is not as good, and clearly there's a systematic problem here. It's not as good, but it's good enough. Again, the important stuff is below maybe 15 kilojoules. The important stuff is here. So now we have a procedure which is practical for, molecules much bigger than this, but if I try to give it 1,000 conformers, that's still a giant job. So it's not really satisfactory yet. So there's a solution to this, and with Spartan'18 we actually have implemented this. We've implemented a very general but also easily very specific procedure that takes the first step is a mechanics step, which is a general, give me the limits of what's possible and what's not, and then ends up with a good step. And it's a multi-step procedure, which the purpose is to gradually go to better and better theory, but as you go to better and better theory, gradually reduce the number of structures you have to entertain. Let me show you what the protocol looks like. It starts from mechanics. It does a search and then very generously throws out very little. It then cleans up the structures with a very simple Hartree-Fock method, and mainly that's to remove duplicates. Mechanics has an issue of generating lots of things that are very similar, and they're really the same. You now you calculate energies with a much better method than either of these, but you now recalculate geometries, and you finally recalculate energy. So we're 5 steps to get exactly, hopefully, the same result as if you did this giant thing right at the very beginning. It's not going to be 100% perfect, but it probably is getting pretty close to that. How does it work? Well, you can see the idea here is that if I just take a couple of molecules I drew randomly, and you see that I start out with this object here. This is tiny, 49 structures. And by the time I'm done, I only have to worry about 14 of them. Or I start out with, I think it says 603, and by the time I'm done, I have to worry about 5. This is completely automatic. So the idea here is that one can put in something, start with it, I'll show you this in a second, put in something, start with it, and then automatically come to a final result. A lot of computer time, but no human time. Or let me do a quick demonstration of that. So if I just build anything, let me start with something really simple. I'm not going to be particular. something. Okay, when we come out here, we're going to have you can sort of see that there's a conformational marker here, and you'll have this is a ring puckering. That's a twofold rotation. We can change it if you want to make it something other than that, it's fine. Or you can get rid of it. So basically, here, one would go in, and one could previously do this with mechanics. Before, you could come in and say, I want to do equilibrium conformer with mechanics, and that's what you could do, and that would be fairly fast. But now you can basically say, I want to do it with density functional theory. What I'm going to select here is I'm going to select one. That one is going to give me, here's my final step. And it's saying, get me the best conformer or distribution. Get me the best conformer at that theory using finally this simpler geometry. Now, what is it actually doing? Well, if I click on details, what it's actually doing is that. It's doing a mechanics search. It's doing a Hartree-Fock optimization. It's doing a density functional energy. It's doing a density functional optimization, and then it's coming back and doing the final density functional energy. So in one step, this will submit a job which will have many, many steps. It may take a long time, but to me, human time is far more important than computer time. In the early days of my racket, computer time was the rather serious. Now it's almost a minor concession. So one can do that. One could also, instead of generating that, you could say conformer distribution, the same thing. You could do it with mechanics, just as before, or you can do it with the same idea here of do it with a good method, and it's going to do the following steps. All of this is completely general. There's nothing that is at all specific to these specific methods. I can replace any step by another method. They're not documented, but it's completely flexible. I can also skip the mechanics search. So instead of coming back here, instead of saying I want to start from the mechanics search, I could start from my own list of conformers. So if I had, let's just make a list by doing I'm going to do a mechanics search. Let's do a conformer distribution mechanics. Submit it. Shouldn't take more than a few seconds. Okay. When I do that, I'm going to get a list of molecules. And I could take that list. I have a list of 18 molecules. I could take that list and I could put in what are the relative energies here. This is all old stuff. And so let's say I really didn't want to consider them. I only wanted to consider the first 10 or 11. 10, just pick a number. I could copy that list. I could go back into the original job, and I could now say, all right, now let's do the distribution with density functional at this. And now instead of this, let's use a custom structure list. And so just paste it in there. So I'm now going to start with the conformers that I generate from some purpose, from whether it's I generate from a previous run or something. It doesn't make any difference. I'm going to start with that. And it's going to, in effect, what it's doing is it's eliminating the first step. It's eliminating the conformer search, and it's starting with a list. The methodology has been calibrated to actually two methods, which we've documented carefully that they actually work pretty well, but it's completely open. If you really like to use B3LYP, fine, you can use it. You can do whatever you want.